Nothing like starting off a little bit with a little bit of technical difficulty. So just a little bit about me and my work history and some obligatory legalese. Like the introduction said, I'm application security focused. I started as a web application developer and sysadmin. I moved on doing DevOps, and then I've done a lot of other duties as assigned, things like incident response, etc. The legal stuff, this presentation is personal work. The views expressed do not reflect those of Truist or BB&T or any other entities. All the photos used are believed to either be mine or public domain. These are my co-presenters for the evening. On the left is Munu, who may break in with an exciting announcement about advanced persistent squirrels. On the right is Duck, who may just complain that I'm not currently petting him. To let you know what this talk is going to be about, I'm going to start with 5 questions. So the first question I started with is, am I or my organization secure against OWASP top 10 if we have APIs? I work in banking, so we're highly regulated, and we get questions from auditors like, are we defended against the OWASP top 10? And the problem is, or not problem, but the good thing is in 2019, OWASP brought out an API-specific top 10 list. But there's a lot of overlap between the application top 10. There is some overlap between the application top 10 and the API top 10 lists, but really you have to draw from both to get full coverage. So the next question to ask yourself is, do you know how the 2 top 10 lists differ? That's one of the big goals that I hope to answer with this talk. Next question is, which one of the 2 is more important for both testing and defending APIs? And it's a trick question because they're both important. Then if you're used to testing web applications, what do you have to think of differently when you're starting to test APIs? A lot of this talk started as kind of the checklist I developed internally for when I was testing APIs, the things I had to think about differently about API testing versus application testing. Most of the time, it just differs as far as the presentation layer, but there are a few different vulnerabilities that are more common in APIs, and there's a couple other things to keep in mind. So that's another big thing I hope you take away from this talk. Then I don't go into too much detail on it, but I do touch a little bit on each part of how to defend against each part of both sets of the top 10s. I'm a big proponent of the purple team concept. Simply testing doesn't make a company more secure. You have to be able to work with developers and give them some guidelines on how to make things better. And that's how the actual value that we deliver comes to the companies that we work for and the organizations we work with. So this is an example of the top 11 deaths in 2003. It's a little bit morbid, but I wanted to point out that just because something doesn't make the top 10 list doesn't mean it's not important. Hopefully most, if not all of us, care about childhood diseases, even if it doesn't immediately impact us. You can also see down at the bottom that there's not that much difference as far as the impact between 10 and 11. That's 1192 and 1124 per thousands. Those numbers are pretty close. So just because something doesn't make the top 10 list doesn't mean you don't have to care about it. It's also a good example, though, because what your organization cares about may differ based on your infrastructure. So if you don't use databases at all for a particular API, you don't really have to worry about SQL injection. So it's a good example also about how we can do threat modeling to make sure that we're checking for the threats that matter most for a specific test. This, if you're not familiar with it, is the CWE Top 25. It's published by MITRE at this point. And it's an example that just because something's not in a OWASP top 10 list doesn't mean that we don't have to care about it either. And so I'm trying to make the point that it's really important to gather information about all the vulnerabilities, because simply paying attention to one list or another is not sufficient. In some cases, these don't really apply to web applications, like rank number 1 right there, out of bounds, right? That's mostly something we don't care about in the web space because we're not using memory unsafe languages like C. We've moved on to things Python, Java, C#, etc. that takes care of that for us automatically. So unless there's a fundamental problem in the libraries that we're working with or the languages that we're working with, we don't have to care too much about that. But you'll also see number 9 there, cross-site request forgery. That used to be part of the OWASP top 10 that was called out explicitly. It no longer is. So again, just be aware that there's lots of other opportunities to figure out what the risks are, come up with a comprehensive list of what matters for your particular organization and your particular applications as you test them. That's how you're going to deliver the best results. A couple more notes. This is a concepts talk rather than a tool-specific talk. I'm not going to say use Burp Suite to do this or use Zap to do that. It's more about just the general concepts. And it's pretty dry. There's a lot of content that I'm trying to get through that's fairly technical. So there's not a lot of memes. I throw in some jokes and images here and there, but if the idea of just sitting through a PowerPoint presentation is not what you want to be doing with your time right now. Feel free to just go to Twitter, grab a copy of the slides and read them at your own leisure. It's fairly self-explanatory, although I do go into more detail on most of the items than just what's on the slides. So the brief agenda for this talk, I'm going to have a really short overview of what APIs are and some of the technologies that are commonly used. Then I'm going to dive deep into the OWASP top 10 API risks versus application risks. And as part of that, I'll give a little bit of the information about how to defend against each one of those. API, if you're not familiar, obviously application programming interface. Wikipedia has this definition here. It's just talking about how software communicates between different components that are software to software. What we're talking about today is mostly web services, or what I call web services. It's a subset of APIs. Again, Wikipedia has a definition. It's just saying that computers are talking to each other by HTTP as a protocol. OWASP itself has a good definition that specifies, as I talked about earlier, it's a difference about the presentation layer. So when you're doing a conventional web application, you also have the window dressing, you've got the HTML, the information, the CSS, et cetera. APIs don't need that. It's just saying, here's the pure data that you're requesting, and it leaves it to the program that's receiving it on the other end to do whatever it needs to present it. So in some cases, it might need no presentation whatsoever. It might be sticking to a database. In other cases, it might be making an AJAX call to an API, and then it's inserting it to web page dynamically. In other cases, it might be displaying on a mobile app, however that's appropriate. So in other words, web services are a subset of APIs. There's a lot of famous other APIs. There's the Java Virtual Machine. POSIX is used most famously under the Unixes, but Windows has that as well. There's the Windows API itself. GTK is a library, and it has an API for doing all kinds of graphical displays on different platforms. There's basically hundreds of thousands, if not millions, of other APIs out there. For the context of this talk, I'm going to use the term APIs and web services. Also, I'm going to say HTTPS or HTTP, and I could mean either HTTP or HTTPS unless I'm specifically talking about problems with encryption. So be aware that I'm just using them as an interchangeable term for this talk. HTTP has become the lingua franca of the internet. I haven't been able to get good figures, but the vast majority of computer communication over the internet is HTTP at this point. It's not actually great for that. There's a lot of overhead that HTTP was not designed for this type of communication. So there's things that are included as part of what the browsers needed that just aren't needed anymore. Different things like HTTP2, HTTP3, et cetera, WebSockets, they attempted to address some of this. But when it comes down to it, almost all programmers who are doing web development at this point know how to do basic HTTP. Almost all the infrastructure allows for it. So things like your firewalls, et cetera, are expecting plain old HTTP. They may not have rules set up for HTTP2, et cetera. Proxies, load balancers, that kind of thing. They also not support the more modern things. And all the languages support HTTP pretty natively at this point. And so that's part of why it has this dominance over the internet. Just an important note of if you're doing tests that involves APIs, and at this point, almost all tests have some kind of API. It's possible that the APIs that are connected to an external site. So if you start doing SQL injection on an application that you're authorized to test against, if it's sending out those requests to a third-party API, you may be running an unauthorized test against that third party. So it's important to figure out what APIs are used by a platform before starting to test. Not only are they the legal issues with potentially sending malicious traffic to someone else's API, in some cases there could be fees involved with the APIs. And even if it's a penny or two, if you're doing a typical DAST test, dynamic applications security test, that can involve sending hundreds of thousands of requests, and that does add up. So just when you're doing a scoping document or scoping process for a new application, make sure that you figure out if it's calling any external third-party APIs, or even internal APIs within a company where there may be additional notification that's necessary. Just a little bit about some common API technologies. There's SOAP and REST that most people have heard of probably, and there's Bespoke and a few others. The old school one is SOAP. It's a formal definition. You're either SOAP or you're not. It's all based around XML. This is going to be important because we're going to talk about a bunch of XML specific attacks. It is carrier agnostic. So it's commonly done over HTTP, but you can by protocol do it over any other by definition, do it by other protocols. And what we talk about today will largely carry over to other protocols, but we're just going to focus on HTTP specifically. And it does have optional security features and WS security as part of the definition. So if you need things like authentication, authorization, privacy via encryption, it's all part of what you can do out of the box with the WS security. Rust, on the other hand, it's an architectural style. It's very commonly today, it uses JSON, but it doesn't have to. It is HTTP specific. You could, in theory, put it over other protocols, but nominally it would no longer be REST. And it has no built-in security features whatsoever. The great thing about architectural styles is you can kind of blend them together. So often you'll find things that are REST-y, and so it may not be entirely RESTful, but it comes pretty close. The other thing with architectural styles is it doesn't require good taste, and you'll find that developers sometimes do things and they're not in fully good taste with their development process also. There's a few other. GraphQL is probably the third most common bespoke and other. GraphQL, I'm not actually that familiar with because, again, I work in banking and we tend to be a little bit more stodgy. So we're mostly based in the SOAP and REST world. Facebook is the biggest proponent of it. It's a full-blown query language, kind of like SQL. And the big thing about it is it can gather lots of data with a single query. So in a SOAP or REST type interface, if you wanted to receive lots of information about many users, for example, in theory, you would make a separate request for each. Whereas GraphQL is designed to say, give me all the information about all the users that match this particular thing. Obviously, you can do that sort of thing with some REST and SOAP APIs, but this is what GraphQL excels at. Bespoke is just a fancy way of saying custom, especially with things like AJAX. You don't need a formally defined API many of the times as far as following a protocol or specification like REST or SOAP. And so it's very easy to say, you know, there's these 8 functions that we need to respond with data via API. And so you just build something quickly and easily using something like Flask or using the functionality of PHP or whatever you're working in. There's a few other things like there are formal specifications like JSON API, but they're pretty uncommon in my experience. So one big thing with doing tests on APIs is how do you figure out the information about the specific web services and APIs? When you're testing an application, it's relatively easy to go through and explore the functionality. There's a user interface, you can intuit it, you can look through the source code and find links and that sort of thing. A big problem with doing API testing is you don't have the ability to just say, here's all the functionality, make sure that you're testing all of it. So one of the top things to do is to ask for the developer documentation. That will give you a lot of insight about all the functions, the different paths, the different variables that are used. There's things like WSDL for SOAP, which is a definition file for all of the functionality. There's also WSDL can be used for REST and WADL. I don't see those terribly often. What's more common for REST that I've seen is Swagger/Open API. There's other formats like RAML, IODoc, and others of those. You can do reverse engineering. So if you're doing something like testing an API that powers a mobile application, you can do reverse engineering on the mobile application, pull it apart and find out what calls it's making. One thing that I think is really powerful is piggybacking off the developer's tests. So assuming that they have written good quality API, UAT, SIT type testing for the APIs, if you run it through something like an interception proxy such as Zap, you'll get a really good readout about all of the functionality. Obviously, that's only as good as the test they've provided and created, but you can get a lot of value off of that. And one last thing you can also do is if you read the log files, you can sometimes find out some paths and variables that aren't well documented. So it's really good to do as many of these as possible to get the biggest picture. There are times that you'll find that there's things been added that aren't in the formal documentation specifications, things that were added that were never put into the WSDL, Swagger files, etc. So just building the biggest picture will allow you to do the best possible test. So now we're about to jump into the meat, which is talking about the 3 different versions of the top 10 that we're going to go through today. This kitty's going to get increasingly frazzled as we go. So when I initially wrote this at the beginning of the year, there was only the OWASP 2017 top 10 list for applications and the OWASP top 10 for APIs. But as we'll get to in a moment, there's also the OWASP top 10 for 2021. So there's a few differences there that we'll go through, but they didn't change that much. So we're going to base it mostly around the 2017 application list and the 2019 API top 10 list. So here they are side by side. The first one, which we'll talk about, will be injection. It was ranked number 1 for web apps, but only number 8 for APIs. There's a group of 6 different ones that I grouped together here. There's broken authentication and broken access control, which are related on web apps, and then broken user level authorization, authentication, function level authorization, mass assignment over there on the API side. There's sensitive data exposure, which only appears on the app list. XXE, which is XML external entities, also appears only on the web app list. Security misconfiguration, obviously, is going to appear in both of them. Cross-site scripting, also known as XSS, only appears in the application list. Insecure deserialization, again, only on that web app list. And that one's a little bit interesting because that's one that's pretty commonly found in API use. So again, just because it doesn't make the top 10 list for the API risks doesn't mean it's not a risk for the APIs. Known vulnerabilities only appeared on the application list, and insufficient logging appeared on both. Over on the API side, the unique ones are excessive data exposure, lack of rate limiting, and improper assets management. So, like I mentioned, we got the new version of OWASP Top 10 for 2021 for applications. So a couple things that were notable here: they combined cross-site scripting and injection into a single one, which makes sense because cross-site scripting is just a form of injection. They renamed broken authentication to identification and authorization failures, but they are largely the same. They renamed sensitive data exposure to cryptographic failures. This is an improvement in my view, because that is really what they meant by sensitive data is cryptography specific rather than things like indirect object reference, which we'll talk about in a moment. Cross-site or XML external entities and security misconfiguration got combined. And security serialization got rolled into software and data integrity failures. Known vulnerabilities got renamed to vulnerability and outdated components, but again, mostly the same. Insufficient logging, they went ahead and specified monitoring failures, because it turns out that logging isn't enough if you're not actually doing something based on the logs. You might as well not have those logs other than the incident response process. There are 3 new things that came into the 2021 list. There's insecure design, software and data integrity failures. This was brought up previously with XXE, but there's a lot more to it, so we'll go through that as well. And then there's the server-side request forgery. This one's been pretty notable in some cloud exploits for APIs, so we'll talk about that last. So I said the kitty's going to get a little bit more and more frazzled as we go through all of these. So the first big one to keep in mind is injection attacks. This is a common area where programmers make mistakes, both in web apps and APIs, and testing for it is largely the same between app and API testing. The big thing to keep in mind here is developers often don't do proper validations, annotation on variables they're coming into APIs, because in some cases they kind of trust that the data is going to be safe. They might think that this is an internally only API, so therefore nothing from the outside is going to flow into it. And it's going to turn out in some cases that there are ways to get information to that API. They may think that, well, it's just coming from the web application, which is doing the AJAX calls, and no one's going to take that apart. And we probably all know in this conference that that's not a reliable thing. They may think that the mobile app is making the calls, and therefore it's kind of immutable, and those calls are going to be safe. And it's not that hard for an attacker to go pull that web application, that mobile application apart, and figure out how the API's calls are being made, and then start making malicious ones. You're probably familiar with most of these. SQL injection is obviously one of the most famous ones. Little Johnny drop tables is an internet punchline for many, many years now. There's the similar ones with NoSQL injection, command injection we're probably all familiar with. LDAP injection is a little bit more common in some cases with the APIs, because users don't typically make a lot of raw requests to LDAP by a web app. But if it's something like pulling information into a mobile app, they may be making direct LDAP requests to the server. And XPath is going to be a little bit more common in API testing, simply because it's a XML specific protocol, and because SOAP and potentially REST uses XML more than standard web applications, you're going to see it a little bit more there. XPath injection, if you're not familiar with it, is a query language from XML. It basically lets you run queries similar to SQL on a large XML document, pull information out of it. Again, because so commonly uses it, it's more common these. It's really an uncommon attack, but I have actually seen it once production. My boss actually got really excited and called me over and was like, Joe, we found XPath injection. It turned out to not have any practical exploits because all we could get was completely insensitive information with it. But we're just really excited that we'd actually found it in a production application rather than something that's just written as a test app. Again, you can't specify arbitrary XML documents with it. You can only query a authorized XML document. So unless there's something that's really poorly designed, it's probably going to be low impact, but it is possible. And every now and then you will get that true positive. Some of the defenses for this that are somewhat API specific, somewhat not. Work with your developers, make sure that they understand that anytime something crosses a trust boundary, if you're not familiar with the term, trust boundaries are when data comes from any place that's not trusted. So you might say that this internal database server is trusted and that you assume that all the data in it is safe. That may or may not be a true assumption, but that is within your trust boundary. Whereas anything coming from a user is always crossing a trust boundary. It can never be assumed to be safe. And you might be doing something like pulling in information from an untrusted database server. You might be pulling in something from another untrusted API. Those are all crossing a trust boundary. And anytime that happens, you must either do something like validate or sanitize or escape that data to make it safe. If you're working with SQL, make sure that you're using prepared statements. That's not any different than working with applications. Like I said, this class of attack is largely the same between applications and APIs. And of course, most WAFs, web application firewalls, they're going to have rules for detecting and blocking this sort of thing. So make sure that you've got a web application deployed, make sure you've got the rules set up properly. Something that I've seen way too commonly is people might have a web application firewall set up so that only half the rules are actually set in block mode. They never took the time to fine tune things and put it into deny mode. So if you're defending against this, if you're working with the defender, make sure that the WAF is fine-tuned against all of these attacks. So like I said, I combined the application number 2 and number 5, and then the APIs 1, 2, 5, and 6 into this kind of large idea of broken authentication or access control. Again, the flaws with APIs are kind of similar, where a developer might be kind of blindly trusting the software systems that are talking to the API, and that leads to the security failures. This class of attack is really where penetration testers and application testers earn their paycheck, because a lot of this can't be tested in an automated fashion yet. For things like SQL injection, cross-site scripting, etc., automated tools can do really a pretty good job at finding it, especially if you're combining things like SAST, static applications security testing, and DAST to get better coverage. That sort of thing is not that hard to write automated tests to detect. Figuring out whether broken authentication or authorization has happened really requires human intellect. And digging in here is where we can find some of the really valuable attacks against APIs and both increase the security value for the company or organization you're working for or with, as well as making sure that people understand what value you're bringing to the table at the test. So like I mentioned previously, mobile apps are a big consumer of APIs, and people kind of might assume that they're safe, and it's just not a safe assumption. Beyond the fact that you can tear them apart, oftentimes you can just put an interception proxy between a mobile device and a web service or API and see what the traffic is doing and start building attacks based on that. There's a technique called certificate pinning, which tells the application to only talk to your specific server with a valid HTTPS TLS certificate. That means that the interception proxies won't have the visibility into that. One thing to do, keep in mind, is it only raises the bar. The dedicated enough attacker can take the time to disassemble the app, pull out that certificate pinning, and make it work for them. So it's definitely worth doing, but don't think that it's going to block a really dedicated attacker. So if you're working like in the financial sector, they've got the motivation to go ahead and do something like that. Whereas if you've got just a very small mobile application that might have nothing really value behind it, you can get a lot of value out of this. So a bunch of things that you see with APIs, they may not be properly set up to defend against credential stuffing or brute forcing, or they may have weaker default passwords. If you're not familiar with the term, credential stuffing is an attack where you go through and you might get the LinkedIn data breach that has both usernames and passwords, and you go through and say, does Bob Smith with password test123 have an account here? Brute forcing obviously is just going through and trying like all the standard usernames and all the standard passwords, or in some cases just trying all the passwords. APIs by nature have problems with two-factor authentication. So with things like mobile banking, obviously at this point, we're pushing users to use two factors, or at least something approximating it with knowledge-based answers. APIs can't sit there and look at a hardware security token easily. So a lot of APIs just have a single factor. So you can find weaknesses that are, you may have a really well-defended web application, but there may be an API that has the same functionality that doesn't have two-factor. And if you can guess a username, password, et cetera, or get it through credential stuffing, you can attack it because there's not that second factor. Something that developers sometimes do is they'll put the session tokens as get variables. So anytime that's flowing through something like an external outgoing proxy or internal incoming proxy, it might get logged. So if an attacker can get access to those logs, they can get all of those variables and then steal the session tokens. APIs will sometimes have long-lived session tokens. They may not ever expire. They may have a longer session life than the equivalent web app functionality. So that's another thing to check. Mobile applications may have hard-coded credentials or API keys inside of them. So again, you just disassemble them, pull them out, look for the interesting strings. You can get all kinds of useful information out of them that way and then get it systems. There's a secret zero problem. Secret zero is that when you're working with stored credentials, at some point there always has to be a little bit of trust. So if I have a system that I'm deploying to Kubernetes that's going to make API calls to a third party, it needs to get the key at some point. If I put the key in plain text into that Kubernetes instance, if someone's able to compromise the application and read that key, then they can get access to the key. If I'm using credential store, at some point that credential store has to trust that it's getting a valid request from a Kubernetes instance it's supposed to be requesting it. So if an attacker were able to make an arbitrary request that credential store that looked like an authorized key or authorized request, it could get that key, and so on and so forth. There's some ways around it, so you can have things like a physical token that has to be touched when a server is spun up, and that is allowed. That's what's used to get the key in the first place, but that's pretty rare in most cases because you just can't have someone sitting there physically touching that key to authorize the system every time you spin up a new server. There's sometimes a problem I talked about earlier that developers will assume that an API will only ever be internally accessible and just won't add proper authorization or authentication to it. And lastly, APIs may trust untrustworthy tokens. So this may come up with, you may say, I'm going to have these 4 different external authorization providers over OAuth, and if one of those happens to get compromised, you could have a token that looks perfectly valid to the application, but doesn't turn out to be trustworthy. You could also have a weakly signed JWT, et cetera. So you just have to make sure that you're staying on top of all of these technologies. So you used to do the external authentication and signing in the keys. It's a lot of work. And this is something that you'll find a whole lot more often in APIs than in a conventional web application. So if you're going to start focusing more and more on APIs, getting up to speed with those is recommended. Some other problems. APIs may not validate the authentication or authorization for all functions. Again, this largely comes down to developers either making a mistake that they shouldn't, or simply, again, going and saying that this is only coming from trustworthy mobile devices or whatever. Therefore, we don't have to check it every single time the request comes in. And this has a couple different things it obviously leads to. There's access control bypass, where if there's administrative functions that aren't locked down properly, if they can figure out what those are, they can get to those. There's indirect object reference. This is really common in APIs, where if there's that unique ID that just iterates by 1, and it's not checking to see if the account that's making the request where it has authorization to see it, you sit there and just add 1 to that integer every single time, and you go through and find out everyone's personal information or whatever it has to be accessing. Then you can also do elevation of privilege, where, again, if it's saying that it may be checking to see if there's an if the user has authorization to access the app, but may not be checking to see if there's specific authorization to use that function. So you can jump up and you can get in user level access, then jump up to an admin using this. In some cases, the developers may forget to put authentication on all the HTTP verbs HTTP verbs. If you're not familiar with that term, it's the ones that we commonly use with web apps. Web apps are get and post, but in REST, we also use put, delete, etc. And so they may lock down some of them, but not all of them. Similarly, you may have controls in your web application firewall that only look for post or get, but don't have the others. So that's something to check every time you're working with, especially REST APIs. There's one that's kind of covered by both of those, but it's specifically called out as the API risk number 6. So I'm going to cover it a little bit more in detail. That's VAS assignment. And that's basically based when commonly you've got a framework that will take any user supplied variable and put it into an update, even if they're not supposed to have the ability to do it. So kind of the canonical example is you might have an update function that says, I want to change what the user's name is. And so if you take looking at an application with the data flowing back and forth in your interception proxy, you can see that there's a put request here and it's update user is pretty obvious. And you can guess the name equals Bob. So if you can figure out what the other variables are used are, so if maybe there's a flag called admin that could be true or false, if you just add that additional information, if it's not sitting there and validating whether the user has the permission to do that type of access modification, if it just takes all of those variables and puts them into a generic query that it builds on the back end, you can get a lot of traction with this. So again, it's kind of covered by what I talked about previously, but because it got its own specific finding or risk within the API top 10 list, I wanted to make sure that I explicitly covered how it differs slightly from the others. Defenses against this, like I said, if you're working with a mobile device, use certificate pinning. It's not a panacea, but it's better than nothing. I'm not going to go into all the defenses against credential stuffing, et cetera, but just follow the best practices for passwords and doing things like rate limiting logins. This is well documented. OWASP and many other sites have great resources on how to do this. When you're doing things where you must have API keys that are stored on systems, use credential vaults to make it harder to get access to them, and do things like make sure that your tokens expire fairly rapidly. So if someone does get an unauthorized token, it limits the amount of damage they can do with it. Make sure that you're using random UUIDs, unique identifiers, so that people can't just go one by one up iterating an integer and find lots of records. And the key thing for this is every single request coming in for any information that's not public must check for both the authentication and authorization. You know, there's no way around it. You just have to make sure that every single request is validated. This partially goes back to the problem that HTTP is not the ideal protocol for this. HTTP was designed to be stateless. Every single request is designed to be discrete and independent from everyone else. And so we've got various ways of gluing on session management. In the web app world, we've got cookies, obviously. And we've got things like session tokens that are made with API requests. Because we don't have the ability to just keep an open connection and say, okay, it's been authorized once, keep this connection open and let the data flow back and forth. Every single request using HTTP must have this validation. Sensitive data exposure. This is the one that got renamed to be cryptographic weakness or weak use of cryptography in the 2021 version. It's very similar to doing standard web app testing. It's things like missing encryption. So if you're sending information that's sensitive and it's not going over TLS, you've got a pretty big problem. If you're using homebrewed or weak encryption, one of the biggest things I took away from taking the Stanford online course of cryptography is I should never ever write a cryptographic algorithm. And there's absolutely no shame in that. Some of the best minds for it in the world have written our cryptographic algorithms, use what they do, follow those best practices on a regular basis. The various standards organizations say what you shouldn't use anymore, what you should use as place. Never roll your own, never let your developers roll their own. And then you can have flawed use of encryption. So that could be anything from using a key that you copy off of Pastebin or Stack Overflow that everyone else is using, or you might be using AES in a way that basically doesn't give full protection. The defenses, I mean, basically you protect your data as best you can, make sure that everything is encrypted at rest as appropriate, make sure that the databases are encrypted if that's appropriate. And like I said, just follow the best practices. Don't ever try to roll your own. XML external entities. This is another one that was kind of interesting that didn't make it into the API specific list because again, XML is more common in APIs than many web applications. It was added to the 2017 version of the API of the application top 10 list, and it was one that was rolled into a different category in the 2021 list. It's XML specific, and it's basically just a local or remote file include server-side attack. So if you're not familiar with it, there's a DTD that allows you to say, go out and this is how to validate this XML content. And if you don't have it locked down properly, you can either read information off of the local server or reach out to the internet or reach out into the intranet and receive information that you're not supposed to and retrieve that using it. The defenses are pretty simple. If you don't have a reason to allow DTDs, just disable DTDs entirely. Most languages allow you to do that. And if you do, for whatever reason, have to allow them, just make sure that you validate them for correctness and that they're not making a call someplace where they shouldn't. Security misconfiguration. Again, this is going to be pretty similar between an application server and an API server, so I'm not going to go into everything. If you want more details, you can check out the OWASP top 10 list for both the APIs and applications. But a couple things that you may find that are specific or more common on APIs is the first, that it may not run on the standard port. So in some cases, it may be running on something like 8080 or 81. So if someone put proper security controls on the standard HTTP ports, they may have forgotten to put it on the ones the API is running on. So that may create some risk that is more common with APIs. In some cases, developers may leave verbose errors turned on. So that's something that's generally turned off in web applications for obvious reasons. But if they're making the assumption that only an API and machines can be seeing this, and who cares if they can see that, there's a SQL error coming through, they may get lazy and forget to turn it off. So make sure that that's turned off. And then particularly with cloud APIs, it's really easy to misconfigure some of those settings and create risk. This was one of the things that we'll talk about with the Capital One attack towards the end of the talk. And the defenses are obviously just don't make mistakes. That's a pretty easy one to tell your developers. But basically, if there's any reason why you're deviating from best practices in your configuration, figure out why you're doing it, make sure that there's a good reason. If there's not a good reason, put a halt to that deviation. And if there is a good reason, make sure that you've got compensating controls. Cross-site scripting, again, this is one that was rolled into a different category in the 2021 list, and it does not appear in the API top 10 list. It's not all that common in web services because it's a HTML or JavaScript browser attack, and it's machine-to-machine communication. But you do sometimes see it where you can use an API to execute a cross-site script attack on something like an administrative panel. And so if you can figure out a way that the content that you're putting into a database, et cetera, will be seen by a web browser, you can do cross-site scripting attacks using it. And you can sometimes use this to do things like attack internal systems when that administrator on the intranet logs in, and then you can start using that cross-site scripting that you succeed in doing to attack inside the intranet. Again, if it comes across the trust boundary, as a developer, you have to make sure that you validate, sanitize, escape. And like other types of injection, web application firewalls have pretty well-tuned rules at this point for detecting this sort of thing. So just be aware that, make sure that you've got your WAF turned on and that those rules are enabled and tuned properly. Insecure deinitialization, again, only found in the application list, but something that you'll find in APIs fairly often. It was now the newcomer in 2017, and again, was rolled into a different category in 2021. Deserialization is when you have information that's encoded as executable programming content. So something like the Pickle library in Python. And if you read the Pickle library, it will say never ever trust information that doesn't come from a trusted source with Pickle. And it basically lets you have complex data structures that, for example, if you're using a load balancer and you're bouncing users between different applications, you might serialize data so that application server 1 can pick up right where application server 3 left off on the previous request. The best defense against deserialization attacks is simply not to use it unless there's a really good reason. In most of the cases with web applications, you can figure out other reasons, other ways to not use serialization, at least in data that's ever coming from a user. If it must come from an untrusted source, make sure that you do as much validation, sanitization, et cetera. There's a great talk from ShmooCon that Sergey Bradis and Meredith Patterson did, I want to say in 2014, that talks about how you can never trust information that's Turing complete because there's no way to actually validate that. There's an infinite number of possibilities as far as any Turing complete language. Therefore, you can never 100% prove that something is safe. So again, my best advice is simply never to use deserialization if it's coming from a user, unless there's no other way. Using components with known vulnerabilities. Again, this is not significantly different than testing a web application, but one thing that you do find sometimes is APIs, because they don't think of them the way this operations may not think of APIs the same way they think of web apps. And so they kind of may forget to keep an eye on them. And then the big thing that you'll find here is IoT devices use APIs constantly. And one of the big challenges we have in the industry is that IoT devices may not be patchable, either by design or because the manufacturer may not bother to ever patch them. So you'll have devices sitting on your internet, intranet, et cetera, that may be risky, and there's no way to fix them that have these risky APIs. Again, if possible, the best defense is to simply never use a component with a known vulnerability. If for whatever reason you must use a component like that, make sure that you've got a VLAN to do isolation as best as possible. You can do things like place inline web application firewalls that just completely block all possible access to certain known vulnerabilities, et cetera. And you can use that as a technique called soft patching. Insufficient logging and monitoring. Again, this is going to be pretty much the same between APIs and web applications, but in some cases, companies may log their web services and APIs, or their web services and web apps differently. So you might find that they're doing really good logging algorithms or logging analysis algorithms in the SIM for users logging in via the website, but they may not have that doing that for the API that you're using to log in by the mobile app. So you'll find some weaknesses there from time to time. In some cases, if the API is really chatty and you're paying by the gigabyte or whatever for your SIM ingestion, they may just kind of cheap out and not feed all the data from the APIs in. Obviously, the defense is to make sure that you're logging as much as possible. Even if it doesn't flow to the SIM, if you at least have it, you can do some kind of recovery after the fact. Make sure that the SIM has equivalent rules. If there's an API that does something similar to what the web app does, and if there's a rule created to alert if there's something malicious going on in the web app, make sure that the API has the similar rules, and then ensure that the SOC can and does take the appropriate steps when there's the issue. Yet again, it's no use having data flowing to the SIM if no one's reading it, if no one's taking action. And this could be anything from a training issue to just the SOC staff is overwhelmed. So figure out why they aren't taking the time to read the logs, figure out why they aren't taking action, and resolve that as best as possible. Cat says, we're almost to the end. Things unique to the API top 10 list. There's 3, excessive data exposure. So this is when the API gives out a lot more information and just trust that the end point is going to do the parsing. So the example here is if you've got the mobile app that says, I need to display the list about the user who's logged in, and the API says, okay, well, here's all the information about all the users. And on your side, just filter out all the information that's not necessary and only display what's authorized for this user. You can't trust the endpoints to do this. You always have to make sure that you restrict what is being given out to the base to the absolute minimum of what's required. So yet again, the answer is to work with your developers and ensure that they're not doing that. There's no clever WAF rules that can fix this. There's no clever SaaS detection tools that will fix this. You just have to look at the data and figure out whether there's more information being given out than there's supposed to be. Lack of resources and rate limiting. This is kind of akin to what I talked about with things like brute force login, but it's also just APIs can have some performance hits. So my previous company had an API that if you made more than about 7 requests to it in a second, it would cause the application server to start falling over. If you start with the assumption that users won't sit there and send thousands of requests a second to that API, if you don't put that rate limiting in, you can end up with an intentional or unintentional denial of service here. So yet again, figure out what the minimum requirements are, work with the operations team to tune the rate restrictions to have what's the realistic use case, make sure that the users are not being unintentionally DOSed by your rate restrictions, but that an attacker can't intentionally or unintentionally blow your APIs out of the water. If possible, one thing that's great with cloud native applications is you can have auto scaling and just say, okay, if things are in heavy load, spin up a bunch of new servers. You need to be careful with this because it can get very expensive. So make sure that that's taken into account. Improper asset management. This is when you might have older versions of an API or test API that remain functional, and they either have lack the protections that the production API does or have vulnerabilities. You may have things like test instances that may have guessable paths or host names. As ever, don't do that. And do things like, if you have an older version of an API, it's a pain. We're working with customers who may be used to it, but you have to say, okay, you have to upgrade your mobile device and start using the newer version of the app because it relies on the newer API, so we can get rid of the old ones. If you must keep the old APIs online, make sure that you backport any security fixes to them, and make sure that anything that's a dev test API instance, etc., is locked down properly. New ones for the top 10 list for 2021. And for the moderator, I'm also almost to the end, so I'm aware that I'm right about at the end limit. So insecure design, this is a new one that's talking about pushing design left, pushing application security left, and making sure that security is taken into account from the get-go. There's no formal way of testing this, obviously, but here's what we can do. We can engage with developers early and often. This works best if you're working on a security team for a company rather than something like a contracting company, obviously. You can do threat modeling with the developers to make sure that they understand what the risks are from the beginning. You can create security champions, which means that you give training to the people who do the development to get them really interested and engaged with security. And very often they will advocate for good security from the beginning. And then something that I definitely promote is provide the developers with fun and engaging security training. So we'll probably all have really dull computer-based training where you just click through and click through and click through, and you don't really care and you don't really learn anything. You can do things like there's different training programs that have developers actually hack vulnerabilities and then fix them. I think that that's a lot more engaging, and you get them to understand both the risks and how to fix them. There's number 8 that's new for 2021, software and data integrity failures. Again, this had deserialization that we talked about earlier, but this is talking about things like subverted continuous integration pipelines, so attacking things like Jenkins, could be compromising trusted data. So something that you think is not crossing a trust boundary, if it's a file that's on the file system that's considered safe, an attacker can get access to write to that. They can do things to attack a web app with it, and things like supply chain attacks, things like what we've seen with the NPM compromises, or just getting it to load a malicious library. Defenses, make sure that your CI infrastructure is hardened as much, least access, least privilege, etc. Use trusted repositories to pull in your files from. So don't just pull from a public repository for libraries. Make sure that's been pulled in, and as best you can secure it by scanning signed code for deployment whenever possible to make sure that malicious code can't be substituted for it. Use software composition analysis tools such as dependency check, which is a project from OWASP. It will say you're using this vulnerable library, you need to upgrade it, otherwise you're going to have the struts 2 vulnerability, etc. And when you're thinking about your trust boundaries, always consider how trustworthy it is. In some cases, even when you think it's mostly trustworthy, you still have to do some validation. Last but not least, server-side request forgery. So this was famously used in the Capital One breach. And this is basically just when you can get the server to make a request to a URI that's not supposed to. The way that the Capital One breach worked is there's a backplane API that's used by AWS that the attacker was able to get a server to make a request to. Once you had access to do that, they could pull out the private key that was the key to access all of the information in the S3 buckets. And by grabbing that, making API call by an SSRF vulnerability in the application, the attacker got the key and then used the key to start pulling information from S3. It's a really simple attack once you know how to do it. Very powerful, big financial hit to Capital One, obviously. The defenses, as ever, validate user input. If there's not a good reason for the user to be specifying what server to go to, don't let them. Make sure that if you have the server that's making requests to a URI, make sure that's configured to not follow redirects, so it can't be redirected to something that looks safe, but then goes to an internal privileged URI. Restrict outgoing access from the web servers if there's not any good reason for it to be connecting out to the internet or to your intranet. On the internal servers, block the internal incoming requests unless there's a good reason why the web server should be reaching to it, and harden the internal APIs so the GET requests don't work. So the AWS fix for this was to modify the API so that you can no longer get that data using a GET request. So even when there's a valid reason why that server should be making GET request, you can no longer, if you're using the new version of the AWS API, it can no longer get that data. So defense in depth, make sure that you've got all these taken into account. I'm a little frazzled. Maybe you're a little frazzled. The kid is definitely very frazzled. Bringing it together and wrapping up before the questions. The things I'd like you to take away from this is keep in mind that the top 10 lists only cover the top 10. That doesn't mean you don't have to care about 11, etc. Be aware that there's other lists to think about. Do threat modeling to make sure that you're doing the most accurate testing for the things that you care about the most. A lot of the testing is going to be the same between doing a web app test and an API test, but I find that having a checklist for all these different things I covered made sure that I don't forget something that was specific to APIs or was more common to APIs. Get as much documentation with the developers, get as much information about an API before testing it as possible, and as much as possible, train your developers to not do that. And now we'll get to the questions. I'd like to take a moment to thank both the organizers and the volunteers for the event and you for your time.